Dear students, welcome to lecture 9. Today we will cover about polycyclic aromatic hydrocarbons. So what are polycyclic aromatic hydrocarbons? These are the compounds which contain two or more aromatic rings which share at least two carbon atoms with them. That means they are fused. So here is an example of naphthalene which you have used in the organic chemistry laboratory, and you know this structure very well. This has two carbon atoms shared between the two rings. Therefore, there are two aromatic rings that share at least two carbon atoms between them. Similarly, there is another structure which contains two aromatic rings, that is biphenyl, but you can see here that they don't share two carbon atoms with each other. So therefore, this biphenyl compound is not called as fused ring system, whereas naphthalene and similar compounds are known as fused ring system. So we will study only two compounds containing fused ring system, that is naphthalene and anthracene, and these are their structures. So naphthalene is a fused polycyclic aromatic compound which contains two benzene rings fused to each other, whereas anthracene contains three benzene rings fused to each other. And this is how one would, the nomenclature of the naphthalene as per IUPAC system, where one counts the number of atoms that are not fused first, that is 1, 2, 3, 4, 5, 6, 7, 8, and then at last we count the fused carbon atoms 9 and 10. Similarly, for anthracene we go like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So let us study more about naphthalene and its properties and how it is used in pharma industry. We will take one or two examples of the drugs which contain this aromatic ring system. So to begin with, it has a melting point of around 80 degrees Celsius and boils at 218 degrees Celsius. It sublimes at room temperature and is therefore volatile. It has a very characteristic smell that can be detected at extremely low concentrations of 0.08 ppm. And this is the same naphthalene that we use in the naphthalene balls within our cupboards. So it is quite toxic, especially to infants and children who are under 12 years of age. Their livers are not fully developed and therefore they cannot metabolize naphthalene to non-toxic compounds, and therefore it may add to their DNA leading to carcinogenicity or liver damage. Therefore it is advisable to keep naphthalene and similar products away from the reach of children. And it is easily obtained from coal tar and is the most abundant component of coal tar. It is about 5% present. And here are some of the other derivatives, some of which, like 1-naphthol and 2-naphthol, you have used in the laboratory. With more substitution, we get 1,5-dinitronaphthalene and aminosulfonic acid derivatives. And similarly, with multiple substitutions, you will get the corresponding dinitronaphthalenamine. Especially here is an example of a drug known as naproxen. It is an analgesic which also contains the naphthalene ring system. So let us study more about the structure of naphthalene. Naphthalene is actually a resonance hybrid of the following structures, which can be drawn like this, in which you are only moving the position of the double bonds and the carbon skeleton remains the same. So all the three structures contribute equally, almost equally, to the stability, aromaticity of naphthalene. It is clear that structure 1 and 2 make a larger contribution, because in this the aromaticity of at least one of the rings is maintained. These two rings, their aromaticity is maintained, whereas in the third resonance structure the aromaticity of this ring is maintained. So unlike benzene, all the carbon-carbon bond distances in naphthalene are not identical. So here you will find that some bonds are smaller and some bonds are slightly longer than the others. But whereas in benzene, all bonds have the same bond distance of 1.4 angstrom. Can you explain this fact and derive these bond distances from the typical single and carbon-carbon double bond distances, and the fact that these three resonance structures contribute to the actual structure of naphthalene, which has these bonding distances in it? And we will discuss more on this in the classroom. So let us understand how one can synthesize naphthalene and its derivatives. So naphthalene can be generally synthesized from benzene derivatives using a combination of Friedel-Crafts alkylation and acylations. followed by dehydrogenation. So to begin with, one can start with a derivative like a chlorobutyl benzene, which is treated with a Lewis acid and heated. So an intramolecular Friedel-Crafts alkylation will take place to get the tetrahydronaphthalene, also known as tetraline. This compound is then dehydrogenated in the presence of palladium carbon, and we get the naphthalene. But some other derivatives can be prepared by using toluene, which is treated with succinic anhydride under Lewis acid conditions, and we get the corresponding keto acid, substituted keto acid. This is further esterified using methanol and acidic conditions, and then it is treated with a methyl magnesium Grignard reagent, where methylation at this carbonyl position takes place, and this is in the next step. It is first hydrogenated to remove this double bond, then converted into the acid chloride here, and then treated with the Lewis acid for cyclization, and therefore you will see that it cyclizes at this position to give the tetrahydronaphthalene derivative, but this carbonyl functionality remains on it, so this needs to be reduced, and it is reduced with the help of lithium aluminum hydroxide followed by hydrolysis under acidic conditions, and then it is dehydrogenated in the presence of palladium carbon to give the 2,5-dimethyl naphthalene. Because naphthalene contains aromatic rings, we expect it to undergo electrophilic aromatic substitutions and related reactions, which is quite true, and it has two benzene rings fused to each other. So what do you expect? Does the aromatic stabilization energy of naphthalene, what do you predict about it? Will it be twice that of benzene or more or less? Can you explain that? We see the actual value. We find that naphthalene is less aromatic than twice benzene. That means it doesn't have two benzene rings, which could contribute to the 36 kilocalorie each of the aromatic stabilization energy. If they did so, its aromaticity should be 72 kilocalories, but the actual experimental value of aromatic stabilization energy of naphthalene is only 61.2 kilocalories per mole and not 72. Can you explain this using the resonance structures of naphthalene? So because it has less aromaticity than two benzenes, it is more reactive than benzene, and it therefore readily undergoes both substitution and addition reaction. These we will study next. So electrophilic aromatic substitutions of naphthalene. As we have studied with benzene and its derivatives, naphthalene very easily undergoes a nitration reaction under nitric acid and sulfuric acid conditions, and it also easily adds substitutes bromine if we treat it with bromine and carbon tetrachloride. Here a Lewis acid is not necessarily required because of the increased reactivity of naphthalene, and similarly naphthalene can undergo Friedel-Crafts acylation reaction in the presence of Lewis acid and suitable solvent, and here you will find that in all three cases that are discussed, the C1 substitution product is favored than the C2. Therefore substitution at C1 is favored in the naphthalene ring. So how can we explain this fact that the C1 product is formed in larger amount than the C2? This can be explained by taking a closer look at the structure of the intermediates and trying to understand which intermediates are stabilized by resonance and which are stabilized to a lesser extent. So if we take a closer look at naphthalene and its mechanism of electrophilic aromatic substitution, we will find that there are two different positions available for substitution. All the other positions are equivalent to C1 and C2. So therefore when the electrophile attacks at C1, these 5 resonance structures are possible, out of which only the A and B preserve aromaticity of the one of the rings, whereas in the C, D and D, the aromaticity of both the rings is lost. Therefore, these two resonance structures contribute significantly to the stability of the intermediate. Whereas if we take a look at the C2 attack of the electrophile, we find that only one such structure is possible in which the aromaticity of one of the rings is preserved, whereas all the other 4 structures, resonance structures, have positive charge delocalized within the other ring, or that the aromaticity is not tamed, and therefore the attack at C1 is more favored because aromaticity of one of the ring is maintained in 2 of these structures versus only one structure in C2 attack. So hence a C2 attack is favored. So further we can try to understand what are the effect of substitution on this reaction of naphthalene, and we find that if electron withdrawing groups are substituted on the ring, the rate of substitution decreases, but if electron donating groups are present, then the rate of the reaction increases and the substitution will happen in the ring where the substituent is present. That means if the substituent is present in this ring, then the electrophile is more likely to attack that ring, because this portion of the molecule is better able to stabilize the positive charge through resonance stabilization, like, and contribution from these. When substituents are present at C1, we will get mostly 2 or 4 substituted product, whereas when substitution is present at C2 position of the naphthalene ring, the electrophilic aromatic substitution of such compounds will give only C1 substituted product. This is another assignment question in which I am asking you to write resonance structures which will explain these two facts discussed above. That means write the resonance structures which show that whenever the substitution is present at C1, we will get both C2 and C4 substituted products, whereas when the substituent is present only at C2, we will get only C1 substituted products. Now, what is the utility of this naphthalene and all these reactions? And as I have told you already, that naproxen is one such drug which has two benzene rings fused to each other. That means it is a naphthalene derivative, and it is highly useful as an analgesic and antipyretic, and it can be synthesized easily from naphthol. So we begin with naphthol and do the bromination reaction with a Lewis acid, and it gives us the C1 and C6 substituted dibromo naphthol derivative, which is then treated with the sodium thiosulfate to get rid of one of the bromine atoms. This compound is later methylated to protect the hydroxyl group in the presence of methyl iodide and triethylamine. Then this compound is treated with a Grignard reagent derived from this bromo compound, and we get the corresponding ester of the protected naproxen derivative. This is then simply hydrolyzed to give you naproxen. More details about this reaction can be found in these reference, and further we can discuss more about in the classroom. Then we move to the study of anthracene. Anthracene contains two fused rings. It actually contains 3 benzene rings which are fused to each other, and its resonance stabilization energy 84 kilocalories per mole instead of the expected 108 kilocalories that one would expect if there are 3 benzene rings in it. Similar to naphthalene, we can draw the resonance structure for anthracene and show that why its aromaticity is less than 108 and why it is only 84 kilocalories. And therefore, it will also undergo electrophilic aromatic substitution more readily than naphthalene because of a lower stabilization. And it will undergo addition and oxidation reactions readily, so that aromaticity of at least 2 rings is maintained. So here are some of the reactions of anthracene where if it is brominated, it will get substituted at this and this position, whereas if you treat it with a strong oxidizing agent, the central ring will get oxidized so as to maintain the aromaticity of the both the terminal rings, and this compound is known as 9,10 anthraquinone. And here are some of additional assignment questions in which I want you to find out which reagents and conditions are necessary to perform these transformations. I will see you in the next lecture, which will be on molecular rearrangements. Thank you.